Yes, uniformity of winding affects ground fault circuit interrupter, or GFCI, performance. Ground fault circuit interrupters continuously monitor the flow of current in a circuit and detect imbalances, which could indicate a ground fault. Imbalances can occur when there is an unintended path for current to flow to ground, such as through a damaged appliance or a person's body. The uniformity of winding in the GFCI sense coil is crucial for accurate detection of ground faults. The sense coil is a transformer that monitors the difference in current flowing through the hot and neutral conductors. If the winding is uniform, the sense coil will accurately detect any imbalance between the hot and neutral currents, indicating a ground fault. To measure the sense coil of a GFCI, a multimeter can be utilized. Firstly, set the multimeter to measure inductance. Secondly, disconnect the sense coil from the GFCI circuit. Thirdly, connect the multimeter leads to the terminals of the sense coil. Fourthly, measure the inductance of the sense coil. The inductance should be within the manufacturer's specified range for the GFCI to function correctly. If the inductance is out of range, it may indicate a problem with the winding or the sense coil itself. Non-uniform winding can lead to inaccuracies in detecting ground faults, potentially compromising the safety of the circuit and users. For ensuring uniform winding, firstly, use a winding machine that can provide consistent and controlled tension. Secondly, maintain proper winding parameters such as wire thickness, number of turns, and spacing. Thirdly, inspect the winding regularly for any irregularities or defects. The operation of a GFCI is based on the principle of monitoring the current balance between the hot and neutral conductors. In a properly functioning circuit, the current flowing through the hot conductor should be equal to the current returning through the neutral conductor. The GFCI sense coil, also known as current transformer, continuously monitors this balance. It consists of a toroidal core wrapped with a winding. The hot and neutral conductors pass through the center of this toroid. Under normal conditions, the magnetic fields produced by the hot and neutral currents cancel each other out, resulting in no net current flow in the sense coil winding. However, if a ground fault occurs, a portion of the current will return through an unintended path, such as the grounding conductor or a person's body. This creates an imbalance between the hot and neutral currents, resulting in a net magnetic field in the toroid. This magnetic field induces a current in the sense coil winding. The GFCI circuitry detects this induced current, amplifies it, and triggers the tripping mechanism, which opens the circuit and interrupts the flow of current. The sensitivity of a GFCI is determined by the number of turns in the sense coil winding and the threshold current required to trigger the tripping mechanism. GFCIs are designed to trip at a very low current level, typically around 5 mA, to provide protection against electric shock. The uniformity of the sense coil winding is critical for accurate and reliable detection of ground faults. If the winding is not uniform, it can introduce errors in the measurement of the current balance. This can lead to nuisance tripping, where the GFCI trips even when there is no ground fault, or to failure to trip when a ground fault does occur. Non-uniformities in the winding can arise from several factors, including variations in wire tension, inconsistent spacing between turns, and defects in the insulation of the wire. These non-uniformities can create variations in the magnetic field distribution within the toroid, which can affect the induced current in the sense coil winding. One common type of non-uniformity is uneven spacing between turns. If some turns are closer together than others, the magnetic field will be stronger in those areas, leading to an uneven distribution of current in the winding. This can result in a distorted signal that is difficult for the GFCI circuitry to interpret accurately. Another type of non-uniformity is variations in wire tension. If the wire is not wound with consistent tension, it can create variations in the inductance of the coil. This can affect the sensitivity of the GFCI and its ability to detect small ground faults. Defects in the insulation of the wire can also contribute to non-uniformities. If the insulation is damaged or compromised, it can create leakage paths for current, which can interfere with the measurement of the current balance. To ensure uniform winding, it is important to use a winding machine that can provide consistent and controlled tension. The winding machine should be calibrated to ensure that the wire is wound with the correct tension and spacing. It is also important to use high-quality wire with consistent insulation thickness and properties. The winding parameters such as wire thickness, number of turns, and spacing should be carefully chosen to optimize the performance of the sense coil. These parameters will depend on the specific design of the GFCI and the desired sensitivity. Regular inspection of the winding is essential to identify any irregularities or defects. The winding should be visually inspected for any signs of damage, such as broken wires, loose turns, or damaged insulation. The inductance of the sense coil should also be measured periodically to ensure that it is within the manufacturer's specified range. If any irregularities or defects are found, the sense coil should be replaced. Measuring the inductance of the sense coil is a critical step in troubleshooting GFCI problems. The inductance is a measure of the coil's ability to store energy in a magnetic field. It is affected by the number of turns in the coil, the spacing between the turns, and the permeability of the core material. To measure the inductance of the sense coil, you will need a multimeter that is capable of measuring inductance. The multimeter should be set to the appropriate inductance range. Before measuring the inductance, disconnect the sense coil from the GFCI circuit. This is important to prevent damage to the multimeter or the GFCI. Connect the multimeter leads to the terminals of the sense coil. Make sure that the leads are securely connected and that there is good electrical contact. Read the inductance value displayed in the multimeter. Compare the measured inductance value to the manufacturer's specified range for the GFCI. If the measured value is outside of the specified range, it may indicate a problem with the winding or the sense coil itself. If the inductance is too low, it may indicate that there are broken wires or shorted turns in the coil. If the inductance is too high, it may indicate that there is a problem with the core material or that the coil is not properly connected. In addition to measuring the inductance, you can also use a multimeter to check the resistance of the sense coil. The resistance is a measure of the opposition to current flow in a coil. It is affected by the length of the wire, the diameter of the wire, and the resistivity of the wire material. To measure the resistance of the sense coil, set the multimeter to the appropriate resistance range. Connect the multimeter leads to the terminals of the sense coil. Read the resistance value displayed in the multimeter. Compare the measured resistance value to the manufacturer's specified range for the GFCI. If the measured value is outside of the specified range, it may indicate a problem with the winding or the sense coil itself. If the resistance is too low, it may indicate that there are shorted turns in the coil. If the resistance is too high, it may indicate that there are broken wires or a poor connection. Another important factor to consider is the type of core material used in the sense coil. The core material is the material that the winding is wrapped around. It is typically made of a ferromagnetic material, such as iron or ferrite, which helps to concentrate the magnetic field. The type of core material used can affect the sensitivity and accuracy of the GFCI. Different core materials have different permeability values, which is a measure of their ability to concentrate magnetic flux. Higher permeability core materials will generally result in a more sensitive GFCI. However, they can also be more susceptible to saturation, which can reduce the accuracy of the GFCI. Choice of core material will depend on the specific design requirements of the GFCI. Some GFCIs use air cores, which do not have a ferromagnetic core material. Air core GFCIs are generally less sensitive than those with ferromagnetic cores, but they can be more linear and less susceptible to saturation. The performance of a GFCI can also be affected by external factors such as temperature, humidity, and electromagnetic interference. Temperature changes can affect the resistance and inductance of the sense coil, which can alter its sensitivity. Humidity can affect the insulation resistance of the coil, which can lead to leakage currents and nuisance tripping. Electromagnetic interference can induce currents in the sense coil, which can also cause nuisance tripping. To minimize the effects of external factors, GFCIs are typically designed to be shielded from electromagnetic interference and to operate within a specified temperature and humidity range. Some GFCIs also include compensation circuits to correct for the effects of temperature and humidity changes. In addition to the sense coil, other components of the GFCI can also affect its performance. These include the tripping mechanism, the amplifier, and the power supply. The tripping mechanism is responsible for opening the circuit when a ground fault is detected. It must be reliable and fast-acting to provide effective protection against electric shock. The amplifier is responsible for amplifying the signal from the sense coil so that it can be detected by the tripping mechanism. It must be linear and have low noise to ensure accurate detection of ground faults. The power supply provides the power to operate the GFCI circuitry. It must be stable and reliable to ensure consistent performance. Regular testing of GFCIs is essential to ensure that they are functioning properly. GFCIs should be tested at least once a month using the test button on the device. The test button simulates a ground fault and should cause the GFCI to trip. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. In addition to monthly testing, GFCIs should also be tested after any electrical work is performed in the circuit. This will ensure that the GFCI is still functioning properly after the work has been completed. GFCIs are an important safety device that can help to protect against electric shock. They should be installed in all areas where there is a risk of ground faults, such as bathrooms, kitchens, and outdoor areas. By understanding how GFCIs work and how to test them, you can help to ensure that they are providing the protection that they are designed to provide. The impact of winding uniformity on GFCI performance cannot be overstated. It directly affects the accuracy and reliability of ground fault detection, which is critical for preventing electrical shocks. A non-uniform winding can lead to several problems. Firstly, reduced sensitivity. The GFCI may not detect small ground faults, increasing the risk of electric shock. Secondly, nuisance tripping. The GFCI may trip unnecessarily due to minor imbalances in the current, causing inconvenience. Thirdly, inaccurate readings. The sense coil may provide false readings, leading to incorrect interpretations by the GFCI circuitry. Fourthly, compromised safety. The overall safety of the circuit and the user is compromised if the GFCI fails to operate correctly. Maintaining uniform winding is essential for ensuring the proper functioning and reliability of GFCIs. This involves careful attention to detail during the manufacturing process, regular inspections, and adherence to proper winding techniques. By understanding the importance of winding uniformity, manufacturers and users can take steps to minimize the risk of electrical shocks and ensure the safety of electrical circuits. The importance of regular testing cannot be overemphasized. Testing ensures that the device is functioning as intended and provides a critical safety net against electrical hazards. There are a couple of methods available for testing, one being the built-in test button, which is the simplest method. Pressing this button simulates a ground fault, triggering the GFCI to trip if it's working correctly. This test should be conducted monthly. Also, using an external GFCI tester provides a more comprehensive assessment. This device can measure the trip time and trip current, ensuring they fall within acceptable ranges. This test should be performed periodically, especially after any electrical work. If a GFCI fails either test, it should be replaced immediately to ensure continued protection. The information provided is intended for general guidance and educational purposes only. Always consult with a qualified electrician for specific electrical work and safety advice. Working with electricity can be dangerous, and it is essential to take proper precautions to prevent electrical shocks and injuries. Ensure that all electrical work is performed by a licensed electrician who is familiar with the applicable codes and regulations. Always to energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, do not attempt to do so. Contact a qualified electrician to perform the work for you.